It is now my pleasure to introduce our second keynote speaker. We had our first keynote speaker earlier with Fran Bagenal. Our second keynote speaker is Stella Ocker. Stella is a doctoral candidate at Cornell University, where she is studying the interstellar medium, pulsars, and fast radio bursts. She earned a bachelor's degree with honors in physics in 2018 from Oberlin College, where she studied the scintillation of signals from pulsars. She has recently published some groundbreaking results using data from Voyager, and today she will talk about the interstellar turbulence near the heliophysics boundary.
Thank you so much for that kind introduction, and thank you for inviting me to this workshop. I'm really excited to be here. It's my first time at an Interstellar Probe workshop. So last year, I actually joined the Voyager team along with my advisors, Jim Cordes and Shami Chatterjee, through NASA's Outer Heliospheric Guest Investigator Program. But a bunch of the work that I'll talk about today was done in collaboration with our colleagues at the University of Iowa, Stephen Spangler, Bill Kurth, and Dawn Gurnett. So if you go to the next slide. So since I haven't met many of you before, I wanted to briefly place in context my motivation for direct sampling of the very local ISM with Voyager or an interstellar probe. So the broad theme of my research is radio wave propagation through plasma in a wide range of astrophysical environments. This includes the very local ISM probed directly by Voyager, to the ISM of the galaxy as a whole, as probed by propagation effects experienced by pulsar radio emission. This also includes direct sampling, well, not direct sampling, in situ sampling of density fluctuations in the interstellar environments around pulsars through their bow shocks, which I'll talk a little bit more about later. And I'm even interested in studying plasma in other galaxies and in the intergalactic medium by taking advantage of the propagation effects experienced by fast radio bursts. And all of this work actually ties together with pulsar timing efforts to detect gravitational waves through the nanograv collaboration, which I'll explain a little bit more in a few slides. So if you go to the next slide. So this broad research theme actually ties directly into these pressing research questions that will be answered in part by an interstellar probe. These are, how does the solar system's interstellar environment compare to other regions in the galaxy? What are the energetics of the ISM from kilometer to parsec scales, both in terms of turbulence and deterministic processes? And how do these energetic processes drive density fluctuations in the ISM? And I want to emphasize that answering these questions really requires complementary studies, both of the very local ISM and studies of remote astrophysical objects. So next slide. In fact, all of these research questions actually tie together in a somewhat non-intuitive way to the pulsar timing effort to detect gravitational waves, which is one of my personal motivations as a researcher. So pulsar timing is very close to detecting low frequency gravitational waves, which are produced by supermassive black hole binaries across the universe. But performing this very difficult detection requires a detailed accounting of plasma along the entire lines of sight to pulsars in a pulsar timing array. And this includes understanding the effects of the very local ISM on pulsar propagation. So next slide. So how do we actually study plasma in the very local ISM with Voyager? Well, today I'll focus on our work with the plasma wave system, or PWS, which we use to study the properties of the plasma density. So the PWS wideband receiver records the voltage difference across the Voyager 1 antenna as a function of time, and then we convert these voltage time series into frequency time dynamic spectra of the electric field through Fourier methods. And these Fourier methods give us a lot of flexibility in tuning the frequency and time resolution of those electric field spectra. So next slide. So here I'm showing you an overview of all of the data that was recorded by the Voyager 1 wideband receiver since Voyager 1 crossed the heliopause in 2012 through early 2020. And so in the top panel, you can see the relative electric field intensity as a function of frequency versus time. And on the bottom panel, you can see a schematic diagram that points out a number of features in this PWS spectrum. So the main feature that you'll notice are these bright bursts of power in the PWS spectrum, and these are the plasma oscillation events that are triggered by shock waves coursing out through the heliosphere and actually into the very local ISM. And by tracing the lower frequency cutoff of these plasma oscillation events, we can measure the plasma frequency and infer an electron density, which is shown on the right-hand axis. And so Voyager 1 has actually relied exclusively on the fortuitous detection of these plasma oscillation events in order to infer the plasma density along its trajectory through the very local ISM. And when I joined the Voyager team last year, one of my first goals was to try and extract as much density information as possible out of the PWS spectrum. So if you go to the next slide. So this past year, we actually learned that Voyager 1 has been detecting not only plasma oscillation events triggered by solar activity, but also very weak persistent plasma waves in the very local ISM. So in the top panel of this plot, you can see the same PWS spectrum, but now we're looking at data between 2015 and early 2020. And in the middle panel, you can see the same spectrum, but now we've applied a different color stretch. So we're looking at the behavior of the PWS spectrum just above the noise threshold of the data. And you can just barely see this very faint line start to appear in the PWS spectrum. And this faint signal really pops out when you look at the bottom panel of this plot where we've smoothed the spectrum in time. And so now we can see this very faint, very narrow band plasma line appear in Voyager 1's PWS spectrum. And so this discovery was surprising because this persistent plasma line appears to be distinct from the plasma oscillation events, not only because of its very narrow frequency bandwidth and its very low amplitude, but also because it actually persists in between plasma oscillation events that were previously discovered, and it persists in the absence of those plasma oscillation events in the more recent data. And so put together, this all implies that this persistent plasma line is distinct from shock-triggered plasma oscillation events and enables a near continuous sampling of the plasma density when we can measure it. So next slide. So this discovery was featured in the August issue of Nature Astronomy, but it left open a few major questions. The first being, why do we begin to detect this weak persistent plasma line beginning sometime between 2015 and 2017 and not earlier in Voyager 1's journey through the very local ISM? It's unclear when exactly Voyager 1 began detecting this persistent plasma line, largely due to the large amount of plasma oscillation event activity that you can see in 2015 and 2017. But to the best of our knowledge so far, Voyager 1 has not detected this weak plasma line earlier. And so the detection timeframe remains a big open question. The second open question is, what is the physical mechanism that is producing this weak plasma line? So if you go to the next slide. So Stuart Bale talked about this a bit in his talk yesterday, so I won't reiterate too much, but a recent paper led by Don Gurnett and his colleagues has provided two main plausible explanations for these open questions that I've just described. So the detection timeframe may in fact be related to variations in the direction of the PWS antenna axis relative to the magnetic field direction. This is because these plasma waves correspond to electric field fluctuations that are aligned with the magnetic field. And so for a very weak signal, we expect that the signal to noise ratio will be maximized when the PWS antenna is actually aligned with the magnetic field direction. And the analysis of the angle between the PWS antenna and the magnetic field direction actually corroborates this explanation. The second possibility for the physical mechanism producing this persistent plasma line is just as Stuart Bale described in his talk yesterday. it may be quasi-thermal noise, or QTN, which has been detected on a number of solar system missions within the heliosphere. But Voyager 1's antenna is far too short to detect kind of classical QTN that corresponds to a Maxwellian electron distribution. And so if this is in fact QTN that we are seeing with Voyager 1, then this requires a significant population of superthermal electrons in the interstellar plasma. So this plot on the right is again showing you an example of what the QTN spectrum could look like with this superthermal component. So next slide. And in fact, we actually continue to see this persistent plasma line through the most recent data from Voyager, and it has turned out to be a really critical source of density information far from the heliopause. So here I'm showing you data from the Voyager 1 wideband receiver now extending through August of this year. And you can just barely see this very faint persistent plasma line persist through 2020 and 2021. And you'll also notice that the temporal resolution of the wideband data is getting worse in late 2020 and 2021. And this is in part due to reduced sampling of the wideband data. And you can see that the amount of sampling that we get is really critical to resolving this really faint signal, but we are constantly trying to improve our signal processing techniques to really optimize our detection of this really faint plasma line. Now you'll also notice that the persistent plasma line reveals this really intriguing density jump in mid-2020, which actually corresponds to a pressure front that was detected in the magnetic field data from Voyager 1. And so the exact origin of this magnetic pressure front remains a little bit of a mystery because we don't see any of the plasma oscillation event activity that we normally see for shock waves that originate within the heliosphere. And so it appears that this pressure front may in fact be a structural feature of the very local ISM. So for more on the discovery of that pressure front and its implications, I would point you to this really interesting paper led by Len Berlaga from earlier this year. So next slide. So now I want to transition into emphasizing one application for why we care about getting regularly sampled density measurements. And so one of the reasons is that density fluctuations trace interstellar turbulence and can tell us about the properties of turbulence that are also measured through magnetic field data. And so density fluctuations follow a power law wave number spectrum that is given by this equation on the bottom left. So here Cn squared refers to the amplitude of the turbulent spectrum. Q, the wave number, is inversely proportional to the length scale of the density fluctuations. And beta, the spectral index, is 11/3 for Kolmogorov turbulence. And this density fluctuation spectrum extends from an outer scale QO to an inner scale QI. And so we can use density time series obtained by Voyager to constrain the density fluctuation spectrum. And here I'm showing you two different examples of density time series that we obtain using the Voyager 1 wideband receiver. So on the left, you can see densities that we obtain using the persistent plasma line that I was just showing you. But because that persistent plasma line is so faint, we can only resolve it down to spatial scales of about 0.03 AU. And this is because we have to average the data in time in order to get a high enough signal to noise ratio for that weak line. And on the right, you can see examples of densities that we obtain from high time resolution observations of bright plasma oscillation events. So in these cases, the plasma oscillation events are bright enough that we can actually resolve the plasma frequency down to spatial scales of about 7 kilometers over timescales of a fraction of a second. So if you go to the next slide. So using these density time series, we can constrain the density fluctuation power spectrum for Voyager from spatial scales of kilometers to tens of AU. The density fluctuation spectrum that we infer both using Voyager and complementary observations of pulsars is shown on the right here. And next slide. And so the constraints that we get from Voyager are circled here. So you can see that Voyager constrains the density fluctuation power spectrum at the largest wave numbers, which are shown as the green points. And then it also constrains the spectrum in the mid-wave number regime shown by these blue, orange, and green points. And so one of the main things that we find is that the turbulent spectrum in the very local ISM sampled by Voyager appears to be to have an amplified spectral amplitude relative to the turbulence spectrum that is observed in the broader ISM. And this may be explained by a superposition of solar wind and interstellar turbulence in the very local ISM. Now, we also see a very large excess of power in the density fluctuation spectrum at the largest wave numbers, those green points. And it's unclear at this point whether this large excess of power, which is at the smallest spatial scales, approaching the kinetic scales in the turbulence spectrum, actually corresponds to real physical processes mediating turbulence at these scales. And so I want to emphasize that Voyager and an interstellar probe are uniquely positioned to constrain this high wave number regime of the turbulence spectrum, where our knowledge of interstellar turbulence is still quite uncertain. So next slide. Now I want to transition and demonstrate how complementary studies of pulsars can actually be really useful for placing our observations of the very local ISM in a broader galactic context. And so the first kind of observation I'll discuss are optical images of pulsar bow shocks. So images of pulsar bow shocks can actually be used to constrain the wave number spectrum at the scales that are circled in this plot here. And if you go to the next slide, one of the main pulsar bow shocks that we use to do this is called the Guitar Nebula. So you can see in the top panel here an image of the entire Guitar Nebula in H alpha emission taken by Palomar. And then in the bottom, you can see 3 images of the bow shock nose that were taken with Hubble in 1994, 2001, and 2006. And so we can actually observe the evolution of the bow shock in time, and this temporal evolution of the bow shock morphology actually directly corresponds to density variations in the ISM that the pulsar is plowing through. And pulsars are very useful for this kind of study because they move at very fast velocities. So the transverse velocity of this particular pulsar is about 770 kilometers per second, which means that by observing this bow shock over timescales of just a few years, we can resolve density fluctuations over spatial scales of hundreds to thousands of AU, and over long time spans up to a fraction of a parsec. Okay, so next slide. All right, so the other kind of pulsar observation that I will briefly highlight here is pulsar dispersion, which also constrains the density fluctuation spectrum at the wave numbers that are circled in this plot. And if you go to the next slide. So radio pulses from pulsars are dispersed in frequency versus time space by ionized gas along the line of sight. And the amount of dispersion that the radio pulse experiences, we quantify using dispersion measure, or DM, which is given by this equation in the top left. It's just the integrated electron column density along the line of sight. And so by actually tracing DM variations in time, we can actually resolve density fluctuations and other interesting properties of plasma along pulsar lines of sight. So the 2 plots on the right are showing you DM variations that are observed by the Nanograv collaboration, which monitors pulsars on timescales of years to decades. And in the top panel, you can see 2 different examples of DM variations. In orange, we have DM variations that are consistent with being driven by turbulent density fluctuations in the ISM. And then in blue, we have examples of DM variations that are actually caused by the solar wind. And then in the bottom, we have examples of DM variations that may actually be related to discrete plasma structures in the ISM. And so DM variations can be used to reveal a lot of interesting properties of plasma, not only discrete small scale plasma structures, but also how the conditions of turbulence vary between different pulsar lines of sight, which reveals how turbulence varies across the entire ISM. It can even be used to trace properties of plasma within the heliosphere by looking at solar wind variations and coronal mass ejections. And the last point I want to make is that the exact effects of the very local ISM and the dynamic heliosphere have on pulsar DMs has yet to be fully explored. So next slide. So pulsar DMs are also really useful for mapping out the spatial structure of the ISM. So this spoke diagram on the left is showing you the average electron density along lines of sight to pulsars within 500 parsecs of the sun. And then the 3 lines of sight that are highlighted in red correspond to pulsars within 200 parsecs of the sun. And so we can actually use distributed pulsars across the sky to look at the distribution of plasma in the solar neighborhood. And we can compare these to densities that are inferred from spectral line studies. So this plot on the right is showing an example of the interstellar cloud complex around the sun just within a few parsecs. And so we can use these densities from spectral line studies to actually situate the local ISM immediately around the solar system within a larger galactic context using pulsar DMs. So next slide. So that actually brings me to the end of my talk. I just want to finish up by highlighting that all of these seemingly disparate topics, pulsar astronomy, fast radio bursts, radio wave propagation in general, actually ties directly to the work that we do studying the very local ISM, and is very much related to these questions of how does the ISM behave as a dynamic environment, and how is this heliosphere really situated in a galactic context? So with that, I will take any questions.
That was great. Thank you so much, Stella. So we have about 9 minutes for questions. And I first want to apologize for any confusion I created with my note in the chat saying we will take questions here. What I meant was that we will take questions in this Zoom room before we move to the next Zoom room. So please make sure to put your questions in the Q&A tool. And we have 3 there so far. So the first question is from Marshall Eubanks, and he would like to know if the Interstellar Probe could observe any pulses, such as the bright crab. And if so, if we could maybe do a stereo dispersion measure mapping of nearby blobs.
Oh, that's a great question. So I don't think any of the instrumentation that's currently proposed for Interstellar Probe would be able to resolve a pulsar. Yeah, but that is a really interesting hypothetical question.
Okay, great. All right, the next question is from Niben Sabarianand, and his question is, how is the statistical significance of these signals calculated, and what is its level of confidence compared to ground observations?
Okay, interesting question. So which signals exactly are you referring to in this case?
And go ahead and type that into the Q&A so that we can see. FRBs.
FRBs. How is the statistical significance of a fast radio burst evaluated? Is that, I'm assuming that is the question.
That and UHE gamma rays.
Okay, so I can't speak to the UHE gamma rays. For FRBs, generally, most of the FRBs that we find at this point are extremely bright. So there isn't much question in terms of their statistical significance. They are extremely bright, which is one of the major inputs of how we see such bright radio pulses from sources as far away as other galaxies.
Okay. So the next question is from Senbei Du. Stella, are the Voyager PWS density data publicly available?
Yes, they are.
Okay.
So yeah, they are on PDS, but if you want a more direct link, feel free to ping me.
Okay. Stephen Owino Omandi asked on slide 16 of the presentation which software you used, because he really liked the plot.
Okay. Which one was slide 16? I have to remember. This one.
Yes.
So I used Matplotlib in Python to make all of my figures.
Okay, and then we have one from John Cooper. Stella, important to model limits on superthermal particle flux spectra from ISM magnetic turbulence. It looks more like a comment than a question.
Agreed.
Yeah, so we'll just skip that one. From Seth Redfield, I may have missed this, but how long do you think you will be able to get VLISM density measurements given the current level of telemetry disruption, or if the disruption continues to increase? I'm interested in connecting them with our astronomical density measurements toward nearby stars. And great talk.
Thanks. Yeah, that's a great question, and it's kind of difficult to know because it depends in part on our DSN coverage, which as you can imagine is, a little bit more of a mystery to someone who's lower in the ranks. But I think so far that our ability to resolve this signal has actually been surprisingly good, particularly over the past half year or so. So I would like to think that if we can keep doing things the same way we are, that we will have them for as long as Voyager PWS is operating. That is my optimistic answer.
Okay, so that is all of the questions that are showing up in the Q&A. I do see one in the chat from Jeff Linsky, and he is asking, can you estimate the turbulent pressure in the VLISM and local interstellar cloud?
That is a great question. So I don't have an estimate off of the top of my head, and I think doing that from pulsar observations may require a significant amount of assumption making, but that is something that I will have to look into, whether we can do that.
Okay. And a comment from Bill in the Q&A just about the power on Voyager to run the digital tape recorder in response to Seth's question.
Yeah, thanks, Bill.
Okay, we don't have any more questions. I will give it a few seconds for any more questions to appear in the Q&A. Otherwise, we can break a little bit early and we will move to a new Zoom room. Okay, we do have one other question, but when we are finished, we will move to a new Zoom room and start the next one at 1:30. So the next question that we have is from Parisa Mostavi, and she wants to know if Stella has looked at Voyager 2 data as well.
Yeah, great question. So I haven't looked at the Voyager 2 data in detail yet, but I definitely will. The issue with Voyager 2 is that the wideband receiver on PWS actually isn't operating anymore. And so we have no hope of resolving this very weak plasma line with Voyager 2. So the only instrument that we're left with on Voyager 2 is the spectrum analyzer. And because of the spectrum analyzer's frequency resolution, it's much more difficult to resolve the plasma frequency to high precision. So we can do it by measuring plasma oscillation events with the Voyager 2 spectrum analyzer, but it is a little bit trickier. So that is on the to-do list, but hasn't been done yet.
Okay, and Stephen has re-entered his question that you already answered, so. All right, we do not have any more questions. So I think we will thank our speaker. Thank you very much. That was an excellent presentation, and I really look forward to the work that you're going to be doing in the future.
Thank you.
We will break here and we will move to the other room where we will have our next presentation. Thank you, everybody, for joining us.
Thank you, Kathy. See you all at 1:30.